Okay, this is the review for the first midterm. What you can bring with you to the exam is a calculator, an equation sheet, and pencil or pen. All the writing, all the written stuff will be on the paper itself. The equation sheet's two-sided, can be anything you like. Some people have postage stamp sized images of past questions. That's okay. It's not a problem doing that, but you need to put it together yourself. The material covered is the first 3 weeks plus the first class of the fourth week. So fluid properties, which we touched on in the first week, fluid pressures at a point, and manometry in the second week. Fluid pressures and how they apply on structures by integrating them, which we dealt with in the third week. And then finally, accelerating static fluids, which we talked about in 4.1. There are 3 questions. The exam is 90 minutes long, but you can stay for 4 hours is the plan. So you can do your best work is the basic idea of that. The 3 questions are outlined as defined here. They include the ideal gas law, fluid pressures at a point, and buoyancy in the first question. Calculation on pressures on structures and failure modes in the second question. In other words, resolving forces and then looking at a hinged gate or something like that to say how it failed. And in the third one, linearly accelerating fluids. I'll tell you what is on it rather than what's not on it, but and what I'll go through in the remainder is just the equations that I think you probably need to be able to solve the problems that are outlined above. This video, if you're watching it, is posted already on YouTube, and there are also previous videos for other years that will include kind of a general review of the material in this part of the course, chapters weeks 1, 2, 3, and also the first part of week 4. So we'll just spend time talking about the things that you might want to have for this. In terms of fluid properties, you'll need the ideal gas law. Pressures are related to density, ideal gas constant, and temperatures. We know that pressures and temperatures must be absolute. So make sure that when you use those, you're using absolute temperatures and pressures. And you can also write this if you want in terms of a density, which is a given mass divided by the volume of that container, if you like. And again, the gas law. You can use that to be able to calculate, if you know densities, you can calculate, and volume, you can calculate the mass of gas, or if you know that the mass of gas is constant and the volume is changing, you can calculate a density, etc. And you can use that in a variety of different ways. But the most important thing is to use absolute pressures and temperatures. For fluid pressures, break this off. So for fluid pressures, we always know that the change in pressure with elevation is always equal to the unit weight, which is the same as rho g, which is the same as minus rho g. We also know that in a fluid, as you go horizontally, the changes in pressures as you go in the x direction or as you go in the y direction, so long as you don't move vertically, are equal to 0. And these are always true so long as the accelerations in that fluid are all 0. And that is absolute. We know that what we do with this expression is we can integrate it, and we can integrate it in 2 forms. We can integrate it for an incompressible fluid, And you know that we just rearrange it as change in pressure is equal to minus unit weight times a change in elevation. And if we integrate both sides and substitute a constant, then we end up with pressure is equal to some reference pressure plus a unit weight and a change in elevation going up and down, which we usually call H. H is positive if it is going down when pressure increases, and it's negative if you go up, as we use in manometry, and this is the case for incompressible fluid. For compressible fluid, we can do the same, but we need to use the equation of state, the ideal gas law, to get the change in pressure. And you don't, as it turns out, need that in this particular case. If we are looking at pressures on structures, then we've typically had geometry that looks something like this, where we have a plane that is of some orientation relative to our coordinate system. This is the surface of the fluid that goes along this point. And importantly, we want to be able to understand the magnitudes of the pressures that are acting on this, the size of the pressures, and also where they act. And so in terms of the magnitude of the resultant, we can get as a function of unit weight, the depth of the centroid, and the area of the plate. And so this has some area. The centroid would be at some location in the middle. And I guess we can draw the important geometry of this is that this is the y-coordinate of the centroid. And when we want to calculate the pressure, the force that's acting, or the pressure that's acting at the centroid, we merely calculate the height of that centroid below the surface, which we'll call h sub c. So this magnitude here is the depth of the centroid vertically below the surface, not the slope distance in the plane of the actual plate. So the area is the actual area of the plate, not the projection of the area, but the actual area of the plate, and the unit weight is the unit weight of the fluid which is around it. If we want to know, so this is magnitude. If we want to know where it acts, we have two possible ways of doing that. Let me do this just to make it a bit clearer. The force acts at the depth, the y-coordinate, the resultant acts at this location here, which is the location of the resultant force. And so physically, Fr acts at this point. And so the location of this point, YR, is the slope distance along in the plane of the plate, down from the surface, and it is given by this component y sub c, sorry, y sub r rather, which is equal to the second moment of area divided by the slope distance of this centroid, the centroid of the plate, multiplied by the area of the plate, and added to the value of the slope distance of the centroid. So in other words, this term here, as we've talked about, is the difference between the y-coordinate of the centroid below the surface and this offset. So because fluid pressures increase with depth, and their moment therefore kind of increases, then the location of the point of action is always at or below the depth of the centroid. And so that's what this delta YC term is here. It's basically this length that we have in here. So that's one way to get that. The other way that we can get that is to take moments about something. So if you look at the pressure distribution on a plate, that might be something like this, where these are the pressure magnitudes that are acting on this plate here. Then you can always divide that into two parts and then calculate for those two parts the force that acts on the triangle, the magnitude of the force that acts on the rectangle, prismatic distribution, and the locations of these. If you know those lever arms, so this would be L prismatic, and this would be L for the triangle, then you can always figure out the magnitude of the resultant force, which presumably would be somewhere between these, with some kind of lever arm. I guess that's not going to work out so well. Some kind of lever arm that is LR, I guess. And you just take moments. And so the product of the moment for both of those, for the resultant and its location, is going to be equal to the sum of the triangular distribution, its length, plus the prismatic distribution and its length. You typically know this. For instance, if this is just a uniform distribution, this would be acting at half height, which would be this length here. If this is a triangular distribution for this would be acting at 2/3 height, so you know that. You know the forces just by looking at this prismatic distribution. I guess we also know that the resultant force has to be equal to the sum of the triangular and the prismatic distributions, both of which we know, and so we know this, and the only unknown is this magnitude here. So that allows us to be able to define the location that the resultant acts and also its magnitude. That covers evaluating the locations of where forces act and their magnitude. And I suppose one other important feature in this is if you're looking at, say, some kind of gate that has a hinge, say, attached with some height of water above it, then it's fine to work out exactly where the resultant might act and also its magnitude. But if you want to examine exactly whether this gate is going to open or not, you have to examine it around the correct failure mechanism. So if you want to know whether this opens or not, then you really have to look at it in terms of the hinge maybe that is opening here to be able to figure out whether the forces acting back that are applied on here are countered. And I guess in this particular case, this would open if the resultant fluid pressure force is acting above this hinge line in this particular case. But you need to be able to examine things in the proper failure mechanism if you're doing that. Okay? So that's forces on structures. If we look at buoyancy, We know that for an object that maybe is tethered and there's a buoyant force that acts, that's attached to this, and we could calculate the tethering force, for instance, if we sum forces in the vertical direction. We know that the buoyant force is equal to the magnitude of the volume of the other fluid that's displaced, multiplied by its unit weight. And so if we know the volume of this, and we know the unit weight of the fluid which is displaced, then we can calculate the magnitude of the force which is acting. And buoyant force in a static fluid will always act vertically. If densities of fluids, of gases, are often much lower than densities of liquids, and so if there are liquids in the system, maybe we can ignore those masses of gases because they get completely swamped by the other components. And the reason for buoyancy, of course, is because there's a net difference in forces that are acting on this buoy, if you like, because as you go down in depth, the pressures that are acting on the base are actually somewhat larger than the pressures that are acting on the top of this. And so by looking at the difference between this pressure here and this pressure here, that force, excess force if you like, that's applied over this particular area gives you this buoyant force. And it always turns out to be this expression. If we look finally at accelerating fluids, accelerating static fluid, we can look at the behavior in terms of the expressions we have for changes of pressure in the z direction, which are equal to density times gravity plus any acceleration in this z direction. And we can individually look at pressures in the horizontal directions, either y or x, which are just given by the density multiplied by the accelerations in those directions. And so if we have, for instance, a closed container, and that closed container happens to be accelerating in some fashion, in some direction, and we have a coordinate system which is y and z, which we usually choose, then we can always get the change in fluid pressure in that system by knowing what the horizontal acceleration is. And so we know that if we plotted across this length of the tank, and we could reference the fluid pressure to some magnitude P0, we can always get the change in fluid pressure, dP dy in this particular case. So this is just the pressure changing as we go across the tank. And if we just look at an individual triangle that represents this, then this would be distance in the y direction, and this would be how pressure changes. So we know that the isobars in this tank are going to be inclined because it's moving. It's basically bulldozing this at the back. If it's closed, the water has nowhere to go, and therefore this has to be the fluid pressure distribution, which is given by this magnitude here. And so if we want to calculate the fluid pressures as they change, we could take, for instance, the magnitude of the fluid pressure and just rewrite it as this. And we could integrate both sides to be able to come up with a relationship which, for instance, is not very different from what we just did So we should be able to calculate exactly how pressures change. And of course, if you look at previous examples, you can calculate the pressure along the back of this tank, and that would be the force that would be applied. I think there was one with a moving truck at some stage that was done in that. So that's one way to be able to look at these behaviors. So this is a closed tank. If you have an open system, and for a closed tank, you need to have some kind of fluid pressure defined somewhere that allows you to be able to map the fluid pressure from one location to another. If you have an open tank, you don't have such a problem in that the fluid pressure is set for you by the location of this back wall. And so in this particular case, if you happen to be accelerating in the positive y direction and you start off with some tank that is filled, then you'll lose fluid, but the fluid will be set by this elevation at the back of the tank, and the change in the elevation of this surface is given by this manipulation of these that we have attempted before, and that is that the change in elevation in the z direction as you go in the y direction is just equal to minus the horizontal acceleration divided by gravity plus whatever the vertical acceleration is, with a negative sign. And so this gives you the inclination of this surface here, and this surface is actually the same inclination as the isobars that would develop in this, which actually are the same as the inclination of the isobars that you'd have in this system. They're directly analogous because the acceleration that you're driving in this case is given by this, and in this case the free surface is what gives you this distribution of pressures. And so the curious feature for this is that if you had, for instance, a cork that was stuck within this fluid and you released it, it will always take the path that transits the isobars perpendicular to their form, whether it's in this form or not. And so this curious behavior is that if you're dropping this, rather than this merely going vertically upwards, you would actually go at an angle which is going across the isobars as quickly as it possibly can. And that's, I guess that's about the remainder of the review. So I've tried to tell you the things that are on it rather than tell you the things that are not on it. The things that we've not talked about, I guess you can probably fairly assume that they don't turn up on the exam, because certainly the equations that you have that we've talked about here are definitely sufficient for you to be able to complete the test. Okay? Good luck. Thanks.